Hi, my name is Evan Nixon, and I'm a senior software engineer at MongoDB. I've been working on Atlas Search for about a year and a half, and I'm here today to talk to you about why text search is important, how full text search works, and how you can use Atlas Search to write full text search queries with MongoDB. So I want to start off with a little bit of motivation. We all probably remember a time not too long ago when websites were a little bit less likely to do things well. You saw a few problems squeaking through the cracks, and there's a skill we've sort of internalized because of this. Uh, One we might not think about very often, but one we use all the time, and that's how to judge the legitimacy of a website. So, to some extent, we have a little bit of our brains that, runs kind of a QA on sites, and when we see a site that looks like this is badhtml.com, you kind of instantly see a number of things that make you they kind of raise these big red flags. This is how we spot spam, and it's something we use to inform our opinion about the legitimacy of a product and a website. There's an old quote by former Supreme Court Justice Potter Stewart that coined the phrase, "I know it when I see it." And I suppose this is my roundabout way of saying, you might not know what exactly makes a good website, but we know a bad website when we see one. And the same is true for search. Users judge the quality of your product based on these kind of intangible things. And one of those things is search results. And these things have been elevated in today's world that makes search table stakes. So the next step here is, well, okay, so we know what's bad. Knowing what's bad doesn't get us very far. It doesn't have that much to do with knowing how to make it better. I know I'm bad at basketball. I know why I'm bad at basketball. Identifying the problems with my basketball game doesn't actually make me better at it. So how do we get better search results? Well, one way to do this is by using a collection of techniques used for searching text called full text search. And that's really what full text search is, a collection of techniques used for searching through text. There are a variety of techniques that we use in full text search. Some of these are linguistic techniques like stemming and normalization. These let us analyze text using strategies that are better suited for different languages or text types. Some of these are more technical engineering solutions. You may have heard the term inverted index. This is a technical solution that lets us run queries that aren't feasible with a regular index structure. And some of these are more of a hybrid. Full text search commonly gives documents a relative score based on how well they fit a term. So instead of your regular query either returning a document or not returning a document, now we've assigned a score, which is how well a document fits a certain query. Before we get into writing queries, let's look a little bit under the hood at what these features do. Language features, for example. Let's look at some of those. Language features use information about how language is structured to change words to a more readily searchable version of themselves. Examples of this are stemming and lemmatization. Maybe we want to deconjugate verbs or remove plurals from words so that they all index to the same variant of a word. Maybe usually when people search for things, they don't only mean to search for runs or running. Maybe they also want to search for ran or a different conjugation. Character normalization lets us strip accents or fold glyphs into common base characters. So this can normalize your character width in some languages, or maybe remove accents from letters because people don't commonly apply accents when searching for things. Stop word removal can exclude common words like that or who, words that don't really have very much semantic meaning associated with them, words that don't help us actually find a relevant document to return. So these language features have a complexity to them. Even something as maybe straightforward seeming as reducing a word to its common root has variations in how you can do it. Stemming and lemmatization apply a similar transformation to words each of them reduces a word to a root that's common to words similar to it, but lemmatization will always create a real word at the other end of the transformation. Normalization is another common transformation. These two character normalizations here are relatively straightforward. We can see all the examples of Canada in the top line here may be lowercase to be a common term, or in the second line, the accents are stripped from the word resume to form a common index term. These are simple here, but they actually can end up being relatively complicated when you consider linguistic differences. Maybe we want to do something more complicated like character withfolding, or there are a handful of other examples. When we consider some of the more technical elements involved in full text search, the first thing that comes to mind is maybe the inverted index. Many full text search engines index using what's called an inverted index. An inverted index's keys are unique words, and their values are occurrence locations in documents. This is a structure that's optimized for retrieval and isn't so different from a glossary. Here's a simple example of an inverted index where each column is a play written by Shakespeare, and each row represents a specific word that might be in that play. When a 1 is in a column, a word occurs in that particular play, and when a 0 is in a column, a word doesn't. You could imagine these columns becoming more fine-grained and maybe representing each scene in a play, and it's not so far from seeing how these become documents. And you might also imagine the number in these columns stops being a 1 or a 0, but maybe now is the number of occurrences in a play, or the number of occurrences in a scene. So now we can start to get statistics. We start to see how frequent a word is, how common it is, and we get a relative number of times that a word occurs in each play. This lets us start to do relative scoring. In full text search, common words count less and infrequent words count more. You can think about this as common words that happen relatively frequently don't give us very much information about what we're looking for. We can also do things like combining search clauses to give those matching more criteria than others a higher score. So maybe maybe a document satisfies some but not all of our input clauses. Maybe we want to give values close to query terms partial credit through fuzziness. So that's really just the tip of the iceberg in terms of what full text search techniques exist and what they can offer you in terms of search. And you can tell that these full text search techniques, they're not rocket science, but they're not so simple either. And if you got into your business to learn a lot about search and have a lot of time and energy to do it, it really is quite interesting, and I would recommend it. But if you didn't, Atlas Search can help you leverage these features quickly and easily and get on your way. So I'll promise now that I'll try not to make this too much of a sales pitch. Atlas Search is a full text search service that runs on Atlas and enjoys a lot of the same benefits that you already enjoy if you're using MongoDB on Atlas. We've enjoyed building it, and we hope you like the features we've been working on. So let's write a few queries and explore some of those features we just talked about. So right off the bat, let's look at some of those language features we can use right now. And to get started in there, let's define a term analyzer. An analyzer is really just a set of sequential transformations. These transformations change input characters into tokens, and they can be as easy as simple splitting on whitespace, or they could be applying more complicated language rules, like maybe stemming in English or normalizing character width in Korean. The goal of these analyzers are to collapse variations in spelling and words that really have a similar concept attached to them to a single semantic representation that we can run an effective query over. So let's look at how we do this in MongoDB. For the sake of example, let's pretend that we're querying an apartments collection holding information about apartments for rent. We're going to build a query here and see how we can execute a full text search query on MongoDB Atlas. So we're going to start with the text operator, and this is sort of the bread and butter of full text search in Atlas. This is going to analyze your query term, and this is going to query analyze text. A sample query over this collection might look something like this. We're querying 4 different words: bright, airy, spacious, and clean, and we're querying path description. The way this query works is that we're going to analyze the query terms and then search for their analyzed forms. So we're analyzing 4 words, running 4 parallel queries for their analyzed forms over index data that's already been analyzed, and then scoring those terms using the strategies we touched on earlier. We'll then return those results in descending score order in order of decreasing relevance. So that's really all we need to do to be able to use a lot of those strategies we talked about earlier. And I want to emphasize that this will get you pretty far. There are a lot of different ways we could do this. And I'm not going to touch on all of them right now, but we could be using other features in the text operator, like using multiple analyzers to query the same field at the same time, and then combining the scores from those 2 parallel queries. We could also be configuring different paths to be analyzed differently. So we might be querying path description with an English analyzer and another path with something entirely different. If you're interested in more detail, here's a link, and that will show you how to set up an index and how to run a text query. One thing people expect when running a search is to be able to run a query that has a small typo in it. If you misspell a single word in your query by a single letter, usually people generally expect that the search engine is able to correct that mistake. So how do we do that? Do we keep dictionaries? Do we maintain larger sets of information that we try to match to? How would we do that for words that aren't in the dictionary, words that are kind of made up internet words? So full text search approaches this by using a term called fuzziness. Fuzziness measures how similar words are to one another, or said differently, how well one word approximates another. Conceptually, we perform a fuzzy search by searching for many variations of a word that are a short edit distance away, where edit distance is roughly the number of edits you need to make to change word A to word B. One edit might be adding or removing a letter. More distant words would have more letters added or removed. So I say conceptually because under the hood, this isn't really how these are executed. We don't run a fuzzy query by generating every possible combination of letters that can be added or subtracted from it and running a gigantic parallel query. In reality, we perform fuzzy queries using what's called a deterministic finite automaton, or effectively a state machine. The image here is a DFA describing the word woof with an edit distance of 1. Edges in this picture describe letters in a word. Darker nodes are accepting states, or states where a word is close enough to be considered a fuzzy match, and lighter nodes are rejecting states. If we want to interpret this graph, we might look at traversing from node 0 to node 7. We see the letter W. That might be a single W in a word, and we note that node 7 is a rejecting state. As we go from node 7 to node 10, we see the letter O is added. Node 10 is still a rejecting state. We're not one edit distance away from the word woof. But when we move from node 10 to node 11 or node 14, adding an O or an F, we see that character strings WOO and WOF are one edit distance away. And by using this sort of a machine, we can tell that if you have a W, an O, and an F in a row, these are actually one edit distance away from our input word. An automaton like this, in conjunction with the trie-like nature of our underlying index, lets us eliminate entire subtrees of our index from the search. This lets us prune off in huge amounts of work, and we end up having to do much less than you might imagine given the previous slide. I'd like to point out here This image is taken from a blog article written by Jules Jacobs, and really would recommend it if you're interested in learning more about the nature of automatons or fuzziness. So looking at our last query, let's add an option and make our input terms allowed to be fuzzy. This is what adding a fuzzy option looks like in Atlas Search. This query is going to quickly build an automaton with accepting states 2 edits or less from each input word. This is a pretty powerful query to be able to run with not a lot of work. We're able to leverage the power of a fuzzy query just by adding an option like this. So given that, we can mitigate some misspellings in a query, but we also want to be able to constrain words to be relatively close to one another. Consider the words dog friendly. We might want to match documents where the words dog and friendly are maybe within a few words of each other. Say the examples on the right half of the screen. Okay, so we want to specify dog is within a couple words of friendly. We can do something like that with the phrase operator. So Atlas Search offers a handful of different operators. Each are a different tool and provide a different set of functionality. The phrase operator in this case lets us specify relative positional constraints for words in our query. So in this case, our words are dog and friendly, and our relative positional constraint is that these 2 words are within 2 other words of each other. So let's talk about that 2. You might notice the slop option in this query, and a longer way of saying that is positional slop. So this is the allowed number of word transpositions or insertions between dog and friendly. So this is a little bit similar to a fuzzy query in a way. Inserting a character in a word costs 1 edit distance. Inserting a word inside a phrase query costs 1 positional slop. Changing the order of words in a phrase query also costs a slop. So like changing the word dog friendly to say friendly dog. And this is going to let us match phrases like dog and cat friendly or friendly for dogs. We can see with just a little bit of effort, we're able to be flexible with spelling, flexible in position, and both in very specified constrained ways that we can tune ourselves. So with a couple lines of code, we've enabled these 2 sets of queries that let us be flexible in terms of matching input to output. And we've started to satisfy more of the types of query that a user is going to expect. But what about combining multiple operators? In the last example, we used 2 operators in isolation. How do we combine those? How do we turn those into a more comprehensive search that only has to run once? Atlas Search lets us combine constraints, like the ones in the last few slides, to perform a single search with results from multiple queries in the same place. We want to be able to join multiple constraints. We want them to be composable, and we're going to achieve that through a new operator called the compound operator. Looking at that last fuzzy query, let's make it a little bit more compact, and let's add it as a predicate inside a new operator. We can combine operators using the compound operator. So in this query, we've taken our last fuzzy query and we've put it inside of a list of should clauses in a compound predicate. The compound operator allows 4 different types of clauses: must, must not, should, and filter. Must clauses are scored and have to match for a document to be returned. Must not clauses are the opposite. If a must not clause matches a document, it's not returned. Should clauses are similar to must, but only one should clause has to match for the compound operator to accept a document. This number 1 is configurable with the minimum should match argument. Filter clauses are unlike the other 3 in that they're unscored. All filter clauses must be satisfied for a document to be returned from the compound operator. However, they do not contribute to the score. So you don't need to memorize all of these exactly to understand what's going on the left here. If you are interested in learning more about these, the documentation is linked below. There will not be a test on these definitions at the end. Here we'll add the phrase operator we created earlier as a must predicate. So each of these two predicates will contribute to the score, and if we add other must predicates, we will still need to be dog-friendly. Using the compound operator, we can combine our constraints. We can determine how we want our documents to have to satisfy those constraints for them to satisfy our query. And we've made this in a way where we can arbitrarily compose different queries to contribute to the score. There may be use cases where you want to limit your query to a particular location. And so let's take a look at how we might incorporate geographic information into search. Looking at our query from before, we'll make it a little bit more compact, and we'll add a new must predicate. Let's say that we want to score results higher that are closer to a particular neighborhood. In this case, we specify a center point that we'd like to be close to Sutro Tower. This predicate credits documents with a location close to that point and decreases that credit as we grow farther away from that point. We can add more geographic constraints, say a filter predicate. Here we can apply a geowithin operator as a filter predicate. This limits our results to within a particular geographic box. In addition to limiting the results we get back, this bounding box will also limit the number of scoring operations we have to do for returned documents. So with a few relatively simple queries, we've now constrained that our results are within a particular boundary, and we've scored results closer to a particular point a little bit higher. To learn a little bit more about how to apply geographic bounds, check out these links. These all link to reference operators that work over geographically indexed data. In addition to geographic boundaries, we can apply other constraints. We might want to specify constraints involving numbers or dates. Again, looking at our last query, let's add another clause. We can use the range operator to constrain numbers as well as dates. Here we apply a range that rent is less than 2,000. We might describe square feet being near 1,200 with the near operator. The near operator has an origin, 1,200, which is the number we're searching for, or the highest scored number, and a value pivot. The pivot value, here 300, tells us that numbers more or less than 300 away from square feet will be scored at 1/2. This is the same as saying 1,200 plus or minus 300 gives you a score of 1/2. We can use those same operators to constrain dates as well. We might want to specify, say, that an apartment is available before a specific date. That was the last addition to our query for this presentation. Through this process, I hope that I've convinced you that search is valuable, illustrated a little bit about what makes search unique, and shown you that using complicated search features doesn't have to be difficult. As time goes on, search isn't going to get less important. People expect more and more from their search every day. I hope you'll agree with me in thinking that Atlas Search is a quick, effective way to implement search in your application, and I hope you'll give it a try. Thanks for watching my presentation.